Good morning, one and all. Thank you for being here. I'm Shree Narayanan from Virginia Tech MEMS lab, and this is a paper on a miniaturized version of a photoionization detector, primarily geared towards gas chromatography. My co-authors are Professor Gary Rice from Department of Chemistry and Dr. Masoud Agah from Virginia Tech, who's my advisor. And to introduce you to what gas chromatography is the science of separating gases and detecting them. And if you can just give me a minute. Uh, Thank you for the invitation. And the science of separating gases and analyzing them. And a typical GC system consists of three main components. The first one is a pre-concentrator. It's an adsorbent bed which can trap the analytes of interest over a period of time. And when it is spiked with a temperature ramp, it's going all the trapped components are going to come out in one sharp plug. And this goes into a microfluidic channel shown on top, where the different compounds interact differently with a polymer coating on the interior surface. So as they travel through, they're going to get retained to different extents and get separation. So what comes out of the separation column are these compounds separated in time and multiple plugs. These are then detected using one among many detectors, and some of these are like TCD, FID, SAW. You'll see a range of detectors out there, and that's going to be the topic of the discussion. Just an introduction to what we do at VTMEMS lab. We work on all aspects of gas chromatography, beginning with pre-concentrator, where we've shown some novel coatings. And stationary phases that are nanostructured, and they are supposed to replace the conventional coatings, and they give a very good performance. And the third one is column architectures. We try to engineer better structures, which are in some cases not possible in conventional gas chromatography. And finally, micro gas detectors. In the past, we have introduced a thermal conductivity detector, as in it's been researched for decades, but what we've tried to do is integrate it with a separation column. And to that end, we started off putting metal on glass and trying to bond it with the silicon. And the reason we do this is we need the silicon to make the separation column, and we don't want to be and to integrate, we want to decouple the process flow. And we've introduced a um, two-port thermal conductivity detector integrated with a stationary phase over here, and we followed it up with an innovative resistor on glass technique, so as to suspend the resistor from glass and give a good performance, as the previous presenter talked about. But there are some inherent limitations with thermal conductivity detector, and some of those are listed over here. Number one, power dissipation. It does consume a lot of power to heat something up to 200, 300 degrees Celsius. Yes, it is probably small, but when it's integrated, you are talking about heating this entire silicon chip. Number two, there's the sensitivity to temperature itself. It is a thermal sensor at the end of the day, so it is going to respond to ambience and programmed temperature effects, which are very critical in gas chromatography. And the response time, there's the thermal inertia associated with a thermal sensor, and the, you, these are not currently in vogue even in conventional gas chromatography. So we wanted to come up with some innovative techniques, something that is going to replace TCD as such in the micro world. So these are some of the ideas that have been explored in literature. What we did was we zeroed in on detecting gases by ionization, and the reason is these are kind of the de facto standard in conventional gas chromatography. And some of the methods that have been explored in the past are fragmentation followed by spectrometric or electric measurements. And the, alternatively, what researchers have tried to do is pyrolyze the analytes in a hydrogen flame, either just directly pyrolyzing it or using a catalytic combustion chamber. But is there an alternative to this? Because one main issue with this kind of detection mechanism, ionization mechanism, is you are going to fragment the molecule. You're going to destroy it. You cannot analyze it further. If you had been to the invited talk, the start of the morning, there was an emphasis on the need for non-destructive detectors so that you can route it on a multidimensional GC. So what we were looking to is come up with a non-destructive, universal, miniaturized, low-part, sensitive detector. So this slide kind of summarizes the motivation and also what constraints the research needed. So number one, we need an atmospheric pressure plasma in a micro cavity. Number two, it has to be low power, and that is something this a plasma phenomenon can provide, because it is high voltage but it is very low current, so it kind of translates to a low power phenomenon. And third, as I mentioned before, you don't want the detector to be sensitive to ambient and program temperature effects, and that's something that's an added benefit of using plasma. And finally, reduce sensitivity to bulk. In other words, the carrier gas that the system is using, because you're trying to ionize only the analytes of interest. So what I'm showing over here on the right side is a pulse discharge helium ionization detector that was introduced in 1992. This is not a micro detector. It's used in conventional GC, and it's commercially available. But our aim was to use an operating principle which is similar to it. I'll get to the operating principle right after this fabrication flow, but it's the simplest fabrication flow you could ever find. So essentially, it's a glass-glass bonded structure. So what you're seeing over here is the bottom glass slide, not a slide, bottom glass wafer, which is patterned using lithography and etched in a wet etching solution to form the microfluidic channels. And then you have the top glass surface, which is bonded over here using epoxy currently. But the metal that is deposited on this acts as the electrodes for the detector. And essentially, what we did was to start with, we tried to study what how an plasma or how a plasma operates in open air. And what you're seeing over here is the IV characteristic of a discharge zone in a across a 20 micrometer gap. So essentially, it takes about 550 volts before the space between the in the 20 micrometer zone ionizes, and you get a constant current, not a constant, a linearly varying current flowing through it. So this is how essentially the package device looks like. Uh, let's spend some time on this structure. So essentially, what this is you can see a faint glow over here. This is the microplasma, and the microplasma is initiated between these two electrodes, and they are spaced about 20 micrometers apart. And these are capillary tubes, and you'll get to learn more about it on the next slide. But this auxiliary channel feeds in plain carrier gas, which is helium, and that helium is providing the source for this plasma. And this analyte channel brings in the analytes. What we're trying to do is, unlike prior researchers, we are not going to we are going to bypass the plasma by releasing the analyte down the discharge zone. So by bypassing, we are preventing the analytes from being fragmented by the plasma, and they get photoionized in this region between the bias electrode and the remote sensing electrode. And when these are photoionized, essentially what it translates to is you can measure a current out of it. And finally, everything goes out of the outlet tubing. Now, since these are photoionized, they are not they are not destroyed, and you can still use it for further analysis. So this is a zoomed out view of the schematic or a schematic of the experimental setup. What you're seeing here is essentially this huge rectangle over here is an oven, a GC oven, and we're using the inlets and the commercial FID installed on the oven to verify our setup on the detector. This is a micro separation column. It's fabricated independently, and this chip is connected to inlet A and does the task of separating the gases into the individual or the analytes into its individual components. The individual plugs then travel out of the separation column and into the plasma detector. Inlet B is the one which provides the helium, plain helium for the plasma. But what one should notice is that the analytes that are coming out of the separation column are bypassing the plasma and reaching over here close to the remote electrode where they get photoionized and get recorded on this electrode that's connected to the picoammeter. So for one such detector, what we did was we tried to calculate the response to injection of air, and what we are seeing here is a kind of a linear, not so linear response. And this slide gives a multi-component detection response, and it's verified by the FID as well. What you can see is that unlike the FID, which is a selective detector, the PID is showing a peak corresponding to air. And in terms of limiter detection, what we did was run through different standards, and we got down to 50 ppm of octane in air, and and the signal to noise ratio for that is calculated to be 3. And to conclude, we have an ionization style detector and a photoionization detector to be precise, that consumes just 1.4 milliwatts of power and can go down to 50 ppm and a 350 picogram detection limit. It's a very simple to fabricate detector, and the preliminary results what we have got are very conducive to temperature programming of the column, and we are looking forward to presenting more improved versions of this detector. Thank you.